Hey there, we're learning about pendulums, and it looks like what we ended up with was that our period versus mass really has no effect. Our period versus angle has no effect until we get too big, so no effect, and then definitely for small angles, we're okay. 15 degrees, probably okay. But the one that affects it the most was the length. We ended up with this weird proportion looking thing that goes through 0, 0. And it turns out that that means that the length is proportional to the square of the period, or another way to think about it is the period is proportional to the square root of the length. Okay, what does that mean? Well, we did this with small pendulums, string with a ball on the end. And one of the data points we got was in 50 centimeters, we got 1.41 seconds. This pendulum behind me is 317 centimeters long, measured the same way we measured this one. And so with that information and with this over here, we could use proportional reasoning to actually figure out what the predicted period should be. Pretty cool. So let's try that out. Here's my pendulum. It's a bowling ball in a bag, promise. Hanging 317 centimeters from here all the way to that top point. From a small angle, we're going to release this. It's about 15 degrees, give or take 5. All right. When it touches my hand to where it ends up touching my hand would be 1 period. What time did you get? I bet you anything it was a little bit more than 3.5 seconds. All right, so let's work out the math, our favorite part, right? So it turns out that this is proportional to that. That means that if we take some period, compare it to the square root of its length, we should get some other period proportional to its length as well. And so that means we have 1 right here and we have 2, but we're missing number 2. So we don't know what this is. We can use our mathematical reasoning and say, hey, that will just be whatever this ratio is. Like that, we can do the math like that, or we can kind of think about, hey, T1 is going to be multiplied by the factor that the ratio of L2 and L1, our new length at 317 divided by 50 is how many times bigger the length is. If we take the square root of that factor, because this is the curve, that will be the impact on the period. It will be multiplied by a factor times our original number of 1.41. to get our new period. And we'll verify it with the one that we measured just now in our video. So we go 317 divided by 50. Those are both centimeters, so centimeters cancels out. The factor change is going to be 6.34. 317 is 6.34 times larger than 50 centimeters. So now we still have to take the square root of that to find out how that's going to impact our original time. So the square root of 6.34 is 2.52. That means instead of multiplying by 6.34, our period is not going to be multiplied by 6.34 times. It's going to be multiplied by 2.52 times. This was a factor of 6.34. Right? Multiplied. We took the square root of that, and that was this factor over here. We're going to multiply this by the square root of 6.34. So we can see how that when we multiply by something over here in the length, the period will be multiplied by the square root of that factor. So if this was double, this would be the square root of 2 times more. If this was 4 times more, this would be 2 times more, and so on. So this is 6.34 times more. So take the square root of 6.34. We found that was approximately 2.52. We're going to multiply that by 1.41, and we get our estimated time. Comparing that to our time, we should see how close we get. Let's find out what that is. 3.55 seconds. What do we get? The predictive power of physics is amazing. We have something that's way bigger than what we had in the classroom, and we were able to predict with the 95% or better accuracy how long it would take to swing back and forth. That's amazing. What the physics is going on. See you next time.
What's the deal with the apple in the tree? Why'd it fall and not